Because of their very low acidity, alcohols do not react with an aqueous solution of a strong base to form alkoxide salts. Instead, they react with active metals like potassium and sodium to form metal alkoxides and hydrogen gas. For example, sodium reacts with ethanol to give sodium ethoxide, with the evolution of hydrogen gas. Cyclohexanol and 2-methyl-propan-2-ol, tertiary butyl alcohol, also react with sodium, forming their respective sodium alkoxide salts and hydrogen gas, but less vigorously compared to ethanol. As the size of the R group is increased, the vigor of the reaction decreases. Methanol and ethanol undergo fairly vigorous reaction with sodium metal, while sodium and butan-1-ol undergo very sluggish reactions. With alcohols containing 4 or more carbons, the more reactive potassium metal is generally used to prepare the alkoxide. An alcohol reacts with a carboxylic acid to form an ester and water. The reaction is carried out under reflux and is catalyzed by strong acids such as concentrated sulfuric acid. The esterification of ethanoic acid with ethanol in the presence of concentrated sulfuric acid gives ethyl ethanoate. The esterification reaction is reversible. This means that after the addition of a strong acid to the mixture of carboxylic acid and ethanol, equilibrium is reached. At equilibrium, the remaining amounts of carboxylic acid and alcohol are still appreciable. However, by using a large excess of one of the reagents, either alcohol or carboxylic acid, esters can be prepared by this method in high yield. Also, if concentrated sulfuric acid is used, it absorbs the water produced, and thus helps to promote ester formation. Other examples of esterification are the reaction between propan-2-ol and propanoic acid, which yields isopropyl propanoate and water. Cyclopentanol undergoes esterification with benzoic acid to give the ester cyclopentyl benzoate. Alcohols, like haloalkanes, undergo elimination reactions to yield alkenes. Because water is lost in the elimination, this reaction is called a dehydration reaction. Although sulfuric acid is often the acid of choice for a dehydration catalyst, other strong acids, such as phosphoric acid, can also be used. For example, ethanol, dehydrated with concentrated sulfuric acid, gives ethene. The dehydration of cyclohexanol with 85% phosphoric acid produces cyclohexene. The acid-catalyzed dehydration of alcohols proceeds by an elimination mechanism. In the first step, the hydroxyl group of the alcohol is protonated by the acid. In the next step, a water molecule is removed and a carbocation is formed. The formation of the carbocation is the rate-determining step of the reaction. Finally, the proton, or the beta hydrogen, in the carbocation is extracted by water molecules which act as base, forming the alkenes and hydronium ions. The dehydration of alcohols follows Zaitsev's rule. This rule states that in any elimination reaction, including the dehydration of alcohols, the more substituted alkene is favored. In other words, the carbocation intermediate eliminates a proton in such a way as to form a more substituted and more stable alkene. For example, the dehydration of 2-butanol gives 2-butene as the major product, since it is a more substituted alkene than 1-butene.
There are several common halogenating agents, which convert primary, secondary, and tertiary alcohols into the corresponding haloalkanes. The reaction of an alcohol with a halogenating agent is another example of a nucleophilic substitution reaction. It can be compared to the substitution reactions of haloalkanes.
The reaction between alcohols and hydrogen halides, HX, forms haloalkanes and water. The order of reactivity of the hydrogen halides parallels their acidity. That is, hydrogen iodide is more reactive than hydrogen bromide, whereas hydrogen chloride is the least reactive. The reaction between an alcohol and concentrated hydrogen chloride requires zinc chloride as catalyst. This reaction, also called the Lucas test, is often used to distinguish among the different classes of alcohols. Among the various classes of alcohols, tertiary alcohols are observed to be the most reactive, and primary alcohols the least reactive. Tertiary alcohols are converted to chloroalkanes in high yield within minutes when reacted with hydrogen chloride at room temperature and below. Primary and secondary alcohols do not react with hydrochloric acid quickly enough to make this a practical method for preparing the corresponding chloroalkanes. Even though elevated temperatures are required to increase the rate of reaction, the more reactive hydrobromic acid is used. Similar nucleophilic substitution reactions of the hydroxyl group in alcohols by halogens occur with other halogenating agents. The general equations for some of them are shown on the screen. They differ in their byproducts. Note that 1 mole of phosphorus pentachloride can halogenate only 1 mole of hydroxyl group, whereas phosphorus tribromide can halogenate 3 moles of hydroxyl groups. The formation of hydrogen chloride, which is observed as white fumes upon reaction with phosphorus pentachloride, is a test for the presence of a hydroxyl group in a compound. Thionyl chloride is a useful reagent because the unwanted products, sulfur dioxide and hydrogen chloride gases, are easily removed. Examples of reactions between alcohols with phosphorus halides or thionyl chloride are shown on the screen. Primary and secondary alcohols react with many different oxidizing reagents, whereas tertiary alcohols do not react. Each step in the oxidation reaction involves either an addition of oxygen or a loss of hydrogen. Any oxidizing agent is represented by the symbol O in square brackets. The oxidation of a primary alcohol can be stopped at the aldehyde stage using certain specialized oxidizing agents. For example, pyridinium chlorochromate, PCC. In general, an example is shown on the screen. On the other hand, with oxidizing agents such as acidified potassium permanganate and acidified potassium or sodium dichromate, oxidation of the primary alcohol continues to the carboxylic acid stage. In general, an example is shown on the screen. Reacting a secondary alcohol with a strong oxidizing agent produces a ketone. The reaction usually stops at the ketone stage because further oxidation requires the breaking of carbon-carbon bonds. Various oxidizing agents based on chromium-6 have been used to oxidize secondary alcohols to ketones. The most commonly used reagent is chromic-6 acid. This acid is usually prepared by adding chromium trioxide or sodium dichromate to aqueous sulfuric acid. In general, some examples are shown on the screen. A color change can be a factor which allows us to distinguish a primary or secondary alcohol from a tertiary alcohol in a test tube, because the chromic acid reagent is orange and the chromic 3+ ion product is green. During addition of chromic acid to an unknown alcohol in a test tube, the formation of the green color means that the alcohol is a primary or secondary one. while no change in the orange colour indicates a tertiary alcohol.
To distinguish among primary, secondary and tertiary alcohols in a laboratory, we can use Lucas reagent, which is a mixture of concentrated hydrochloric acid and anhydrous zinc chloride. It reacts with alcohols to form haloalkanes. Alcohols with 6 or fewer carbon atoms dissolve in Lucas reagent, but the respective haloalkanes formed in the reaction do not dissolve. Therefore, 2 phases, or a cloudiness, will be observed during the reaction. The time taken for the appearance of cloudiness in the solution is used to distinguish among the different classes of alcohols.
Let us do a simple experiment to study the effect of Lucas reagent on the rate of halogenation of the primary, secondary and tertiary alcohols which are isomers of butanol. Lucas reagent is a colourless solution. After adding some drops of the liquid alcohol, a haloalkane is formed as a separate liquid phase. The solution containing a tertiary alcohol turns cloudy immediately. After about 5 minutes, the solution containing a secondary alcohol also becomes cloudy. No observable changes take place in the beaker that contains the primary alcohol. In conclusion, the most rapid reaction is given by the tertiary alcohol, followed by the secondary alcohol, which in turn reacts more rapidly than the primary alcohol. We've learnt that a mixture of concentrated hydrochloric acid and zinc chloride as catalyst is called Lucas reagent. This reagent can be used to distinguish among the different classes of alcohol. The measure of reaction rate is the time taken for the appearance of cloudiness in the reacting solutions. An experiment is carried out to identify ethanol, propan-2-ol, and 2-methyl-propan-2-ol using the Lucas test. The solutions are placed into 3 test tubes labelled A, B and C. When Lucas reagent is added to each solution, the mixture in test tube B turns cloudy immediately, while the one in test tube A turns cloudy only after about 5 minutes. There is no change in the mixture in test tube C. From this experiment, the following conclusion can be drawn.